Masterclass, Enabling Safe Environments, Transmission and Mitigation of SARS-CoV-2 with Cath Noakes from Leeds University.
So thanks Azal for asking me to come and talk. So I'm going to talk through some of what we know about how COVID transmits and what we think we can do to mitigate that transmission. And I've got I've got about half an hour's worth of talk, and then we can open up for some questions and things afterwards. What do we know so far? So we know that this is caused by the SARS-CoV-2 virus. We know from a lot of laboratory work that it survives in air and on surfaces. There's not a lot of actual real world data on that yet, though. So we know from it has the potential to survive for a long time, and it will survive in air for several hours, but we don't really know what that means for real world because there's very little evidence from real world settings yet. We know that all the transmission seems to happen indoors. There's very little evidence that outdoor transmission matters unless people are very close together. And we know that transmission is most likely dominated by what happens when you're close to somebody, so short range mixture of droplets and aerosols. And I'll talk quite a bit more about droplets and aerosols as we go through. We know also that there's evidence for transmission in poorly ventilated spaces, which is quite probably where people are further apart, so that's probably an airborne transmission. But we also think that we can't rule out surfaces, and certainly there's evidence that suggests that washing your hands can help mitigate transmission, which tends to then suggest by proxy that there is some contact transmission, and it's maybe something around 20%, but we don't quite know that yet. So actually we're what, 9 months into this now, but there's still an awful lot we don't know. Just to go through the sort of mechanisms around potential transmission, the main source of transmission is respiratory aerosols and droplets. So when we're breathing, talking, coughing, laughing, etc., we're producing these aerosols. They will contain the virus. There's also evidence of virus in feces and in fact in urine as well, but there's very little evidence that there's live virus there. So there's a huge amount found in wastewater, but it seems to just be viral RNA rather than live virus. So it's not clear whether there's any route of transmission there. There's no clear evidence that there is. I think the other main source is the fact when somebody is infectious, they themselves will be contaminated, their hands will be contaminated, they will touch surfaces that might touch people. So then depending on the source, we'll have some different transmission routes. So we'll have aerosols, larger droplets, and surface and fomite. Fomites are objects in the environment, so we tend to call them fomites when they act as an intermediary in transmission. So there are 3 different routes by which something can travel from an infected person to a susceptible person in the environment. And then people may be exposed in different ways. So aerosols, the very smallest aerosols might get inhaled into the deep lung. Larger aerosols might impact in the nose and the mouth. There are larger droplets too, which could deposit on your eyes, your nose or your mouth. But some of those droplets will also deposit onto surfaces, and that creates then a contamination route of surfaces via contaminated hands or fomites. If you touch a contaminated surface, then you touch your eyes or touch your nose, potentially there's a transmission route that way. So this is actually quite a complex set of interactions. There are multiple routes in here that transmission can happen by. We don't know the balance of them. We don't know which ones are most important. We just know that from everything we've seen, these are what's most likely to be the things that are happening. And it's a complex set of interactions based on the virus itself and how that behaves, the environment that it's in, including the fluid dynamics of that environment and airflows and things, and human behavior. So all of this is dominated by how humans interact together. So really quite a complex system. We know a few other risk factors as well. So the close range transmission, we know that the closer you get, and if you're face to face, the chances are that's more risky because you are more directly within the exhale breath of a person. We know that aerosol risk is dominated by ventilation. So if you're in a poorly ventilated space, it goes up, but also if you're close to somebody, that goes up as well. And we also know that in contact transmission, that if you're closer to somebody, you're more in their space, you're more likely to interact with surfaces and things that they touch. And then we also know that duration matters. So the longer you spend with infectious person, the higher the risk is going to be. Really quite important is that some activities such as singing and loud speaking can push up the risk. I'll talk a bit more about that in a minute. And of course, the higher the prevalence in the community is, the greater the risk is of coming across somebody infected. And then there's a little bit more on environmental conditions, in that we know that this virus survives better when it's in cooler conditions, when the temperature is lower, when the humidity is lower, and in dark conditions. So it's in bright outdoor sunlight, the virus will die in minutes. If you're in the UK and it's the winter, the virus will survive quite considerably longer, we think. And then there's a few more complexities to throw in there as well. So it does seem that the highest risk seems to be in the very early stages of disease, and that might well be before people show any symptoms. And we also know that sometimes people don't show any symptoms at all, but asymptomatic transmission can happen. And it's much more likely that happens with younger people than older people. So, which makes it quite difficult, for example, university settings or college settings, where you might have high numbers of people who are infected but have no idea they're infected. And because of that, we also know that you don't need to cough and sneeze to spread the virus, that you can simply spread the virus through normal activities, breathing and talking. We know there's a big inequity in health impacts. So men seem to be more susceptible than women. Once the age is a very big risk factor, but ethnicity is quite a big risk factor too. And there's a lot of issues with underlying health conditions, particularly diabetes and obesity seem to be a big risk factors. And then a really big challenge with how to control this virus is the super spreading. So the virus is very highly dispersed, and basically that means that you maybe have, say, 10% of people could be responsible for 80% of the transmission. So most people don't transmit it, or don't transmit to very many people, but then some people are basically super spreaders, and they're the ones who unwittingly significantly transmit the disease. And then we know that those events tend to happen in indoor, close contact, poor ventilation, crowded spaces. So I had quite a bit about aerosols and droplets. I thought it was worth just talking a bit about what these are. If you look in the dictionary, an aerosol is a suspension of fine solid or droplets in a gas, but a droplet is a very small droplet of liquid, and that's not very helpful. So I think it's worth thinking about size. If you imagine this is a 100 micron droplet, and this is a human hair, so your human hair is about 60 microns, you sort of start to get a first feel of scale for this. When we're talking about the finest aerosols, so a 10 micron aerosol or a 1 micron aerosol, you can start to see how small these are going to be. So when we're talking about, is it a droplet or is it an aerosol? Actually, to be honest, all of these are aerosols because they will all stay in the air for a period of time. Droplets tend to be bigger than 100 microns. I think it's worth looking at how people are exposed. So if you talk about airborne infection, classic airborne infection says a 5 micron droplet or 5 micron aerosol is airborne, and anything above 5 micron is droplet transmission. That's a really outdated definition now, and it really comes from the fact that 5 microns can reach the lung. And if you look at the graph, it sits in what we call the respirable convention, and these are the ones that can up to about 10 microns just about can get to the deep lung. But there are plenty of other aerosols that can be inhaled too. So the thoracic convention, which we'll get into the the top of your lung and the upper parts of your respiratory tract, well, that will down to about 20 microns, you can inhale those. And then the inhalable convention, these are the ones that will deposit out in your nose, your mouth, the back of your throat. You can inhale up to about 100 microns quite comfortably here. So and for some diseases, tuberculosis, the 100 micron ones don't matter because you have to reach the deep lung. But for COVID, it does matter because it basically has to bind with what's called an ACE receptor. And you get those receptors are in your mouth and in your nose, as well as in your respiratory tract and various other parts of your body too. So it really does matter. Of course, if we're thinking about surfaces, I think droplets landing on surfaces, it's really how the bigger they are, the more contamination you'll get, but any size can land on the surface. So I think it's really quite important that we don't just sort of go with the old medical definition of airborne versus droplet. And actually this disease is really making us think that this continuum of aerosols and droplets matters much more than perhaps with the medical textbooks will tell you. Just to give you some data on what we find from people. So this is fairly old data, in fact, it's very old data, but I'm showing it because it's nice. But it shows you just the typical size ranges that you might get in exhaled breath. So on the right is somebody counting 1 to 100. When we've got somebody coughing and somebody sneezing, and you can see the order of magnitude differences in the number of particles that get produced, and the typical size distribution. And the people tend to produce particles in the sort of 1 to about 50 odd microns typically. There's a few that are bigger than that. Actually, we now know that people also produce more finer particles, which we can measure using optical particle counters. But the really fine ones don't matter so much for transmission. It's the bigger ones that count. So these are the ones that are going to matter for transmission. The smallest ones just can't carry enough virus. It's actually quite hard to sample microorganisms. So the data I showed you there was sampling just aerosols. But if you're sampling microorganisms, it's really tricky. And there's a couple of instruments shown here. The one on the right is a relatively crude instrument. This was used to sample for tuberculosis. But the one on the left is a really sophisticated instrument at the University of Maryland by Professor Don Milton's group. And it's basically a condensation aerosol, condensing aerosol counter, which can size segregate virus. And you put your head in the cone in a really quite specialist piece of equipment, and can sample microorganisms in exhaled breath. And just to give you some idea of what this instrument produces, this is for influenza, and it's segregated into below and above 5 microns. And you can see that there's about the same in the coarse and fine fractions for influenza, so they're around about the same orders of magnitude. You can see that it tends to increase with coughing, but what you can also see is there's an enormous range. So you can see that we're going from about 10 to the 3 RNA copies per sample up to maybe nearly 10 to the 8 RNA copies per sample. So that tells you that some people produce very little and some people produce an enormous amount. And that makes life very difficult because we don't know who those people are, and how do you identify them. We know that activity comes into it too. So this is not microorganisms, this is just particle data, but this is measured from people breathing, speaking, singing, coughing, to just show you those ranges. And if you look at the one that says breathing, you can again see that amongst these 25 participants, there's a very big range of droplets produced simply by just breathing. But then when you look at singing, for example, you can see that as the sound level increases, that you get quite a substantial increase, and potentially sort of 20 times as much if somebody's singing loudly compared to if they're quiet. And the same with loud speech. And you have to be a little bit careful with loud speech because 90 to 100 decibels speaking is shouting, basically. So it's not quite so comparable to singing. But you can sort of see why it's going to be quite difficult to work out what's going on with people. The other thing we know is that viral load varies. So this is data from throat swabs and nasopharyngeal swabs. This was taken very early in the pandemic. I think this was published back in April, but this and only from symptomatic cases. But what you can see is that over the course of somebody's infection, the amount of positive culture, the amount of RNA swabs drops off. And if you look at the graph on the right, you can see it drops off quite significantly. So the most hazardous time is probably at the beginning of the disease. People who are in hospital have been sick for a couple of weeks are probably a lot less infectious. They're producing a lot less virus. I'll go back to the aerosols and things. So I mentioned these aerosols is what people produce. What happens to them once they're in the space? Well, they will have forces that act on them. They'll have a gravitational force and a drag force. And so if they're in still air, they will settle depending on the mass of them. But actually air in a real room is not still by any means. And actually there's quite a lot of air movements that can keep these particles suspended for far longer than you think. And even something like a 50 micron droplet potentially can be suspended for quite a period of time, much longer than sort of the basic physics suggests it should do. And if you look at that, this is really simple simulation, but just looking at what ventilation does, you can see in this that the largest particles behave like ballistic trajectories. They're like mini cannonballs and you throw them. But the sort of big aerosols, 100 microns, 200 microns, tend to fall out the air pretty quickly, but they've got a little bit of effect of the airflow. And then once you put once you get to 50 microns, you've actually got quite a lot of movement, and the 10 micron droplet aerosol does not settle. It goes off around the room with the ventilation. So, you know, the medical statement that a 5 micron droplet settles out in a meter is basically untrue. Physics says it just can't do that. Just also now to mention evaporation. So when the virus is only about 100 nanometers, but it's contained within respiratory fluids. And these are actually contain things like proteins, surfactants, salts, and they're much bigger than the virus itself. So these particles, the aerosols and droplets, will start off, say, maybe it starts off at 50 microns. They will evaporate very rapidly when they come into leave the sort of 100% humidity of your respiratory tract and go into the air. But how quickly they evaporate depends on the environment and depends on their size. But it typically happens within, you know, for most of them within a fraction of a second. Even your 100 micron droplet will evaporate to half of its size within 5 seconds. So we need to actually think about evaporation and what's happening to these. And of course, if you start with 100 microns and it evaporates to 50 microns, it basically stays airborne for longer and concentrates the virus. So we need to think about that as we're considering transport of these particles. Just to think a bit now about how we can control the disease. And one of the things we've been advocating for is people think through a hierarchy of risk controls approach. And this is a very standard methodology in risk assessment and thinking about, you know, you start with the first stage, which is elimination. So actually, can you avoid any form of interaction which will allow you to come into contact with somebody with the virus? And of course, something like a lockdown or work from home is a form of elimination, really. And so basically stop doing something. We then think about substitution, and again, things like work from home, but do everything by Zoom is part of that. But then thinking about alternative transport, alternative ways of delivering things, etc. But then once you get to the fact that you need to be interacting with people, then we've got controls that you would place in a building. And engineering controls is a really important part of that. There's a lot of potential for engineering controls. There's a lot of the evidence base is very weak though. So ventilation, screens, barriers, low touch surfaces, automatic doors, that sort of thing, are all potential controls that can be implemented. We've then got a big layer of administrative controls where things like having cleaning regimes, marking out on floors where people can stand, one-way systems, that sort of thing, and all of your protocols fall into this. And then really the last one is personal protective equipment. So ideally this should be the last resort. We are at a position with this where we need this considerably more than we would hope we would, but and it's interesting thinking, where does face masks or face coverings fit into this? I would argue they, to some extent, they're PPE because they are protection, but I think they're also an engineering control because they act as a source control for people in the setting. And we can talk a little bit more about face coverings. We, in the UK, we've tended to use the word face covering rather than face mask to try and differentiate it from surgical masks, which are protected for healthcare workers. So the main purpose of this is it's a source control. So the idea is it can prevent droplet spray. It can also limit the aerosols, because if you think about aerosols being because of evaporation, this mask or face covering can actually capture the aerosols and droplets while they're larger before they've evaporated. And although the main purpose is source control, actually, if you're wearing a face covering, face mask, it will provide you with some protection. Of course, if you don't cover your nose, it provides you with no protection at all because you just breathe in through your nose instead. Respirator masks, so N95, FFP2, FFP3, are all designed as protection, and they're designed as aerosol protection. So I think there are settings when these are important, like in some healthcare settings, but a lot of the time we don't need these because the aerosol risks are not sufficient that we would need these in most settings. And then you also see quite a lot of these face shields, which are about protecting the wearer. So they'll protect you against large droplets, they'll protect your eyes. They will do nothing whatsoever for aerosols. And so they're not likely to work as a source control. And just show you some how a mask interacts with the airflow. So if you look, she's coughing, you can see the thermal plume that goes around her. And then when she's got the mask on, it actually stops that thermal, that plume from her mouth. So it actually prevents the exhalation going as far. And you can also see the effect of masks from biological data. So this again is done in using Don Milton's G2 machine, where he's measured influenza, and he's used a seasonal coronavirus as well. So people infected with a seasonal coronavirus is typically called a common cold. And what you can see is that the masks are really quite effective at blocking both larger and smaller aerosols in here. And they're actually more effective for the seasonal coronavirus than they are for influenza. We don't know yet what this means for SARS-CoV-2. I'm really hoping that Don Milton is, well, I know Don Milton's doing these experiments at the moment. I'm really hoping that we'll see that data soon, because it will then tell us quite a lot more about what's happening. We see a lot about distance, how far apart you should be. So basically, if you're very close to somebody, you're in this sort of cone of fine aerosols and droplets. The further away you go, the lower this concentration is. If you go beyond 2 meters, you're at potential risk of aerosols that have remained in the air if the ventilation is insufficient. Potentially those aerosols could go further, but we don't think that's really happening. We think most of the risk is happening within the same room. This is not like measles, where it goes off around the whole building and can affect people over bigger distances. The physics of distancing, though, is actually quite complex, and there's some really complex fluid dynamics that happens when people cough or sing or breathe. You've got these this exhalation. It's a little bit like a Gaussian plume, but also you've got other weird behaviors that go on, where the droplets can interact together and stay in like what we call a turbulent puff. So it's particularly when somebody coughs, it's a more violent release, and some really interesting work from Lydia Baroba at MIT, who's done some fascinating work looking at how these exhalations travel. So from an engineering perspective, I guess we've talked a little bit already about engineering controls, but we want to basically break that chain, and there's a lot of options in there. So ventilation is a major option. We can use technologies, air cleaning technologies, decontamination and filter technologies and surface technologies that might be able to help us. I think we can also use engineering to actually separate people. And this was written for this slide's written for a hospital, but you can actually use engineering to control the movement of people and their interactions in a space. I'll talk a little bit about ventilation. So we can actually try and look at the relationships between airflows and risk for the airborne component. We can use something called a Wells-Riley model, which can relate the number of new infections with how many people are susceptible and the number of infectors, the ventilation rate, which is this one, capital Q, and how much people breathe, and the generation of infectious dose, which we call quanta. And basically this term here is like a concentration that people inhale with time. And what you can see is if you actually start looking at this, we know that there's so much variability between different parameters. It's quite hard to put a sort of single simple value on it. But what we can say is that one of the biggest parameters is going to be the emission rate of infectious doses. And if somebody's only generating 1 quanta per hour, you can see that the risks are very small, and they only really go up if the ventilation rate's very poor. But if you've got somebody who's generating 100 quanta per hour, you can see that we end up with some really quite high risks. And even with quite good ventilation, the risks might still be high. What we don't know yet is how likely these are to happen. We know that we suspect that 1 quanta per hour is far more likely than 100, but we don't quite know yet when and where these settings may take place. And for example, this may equate to singing in poorly ventilated settings. We just don't know. This is Zail's favourite topic, germicidal ultraviolet. So if we can't ventilate a space well, then germicidal ultraviolet might be one of the options we can apply to mitigate risk. It works by using ultraviolet C radiation. If it's it basically inactivates pathogens. And it depends on the type of species, it depends on the climatic conditions, it depends very significantly on the UV dose. There isn't any actual data yet for SARS-CoV-2. I think there might be some lab data of inactivation in cell culture, but there isn't any in air yet. However, we know that other coronaviruses are inactivated in air. We know that SARS is inactivated, and are both, and it's fairly easy to inactivate. So it's a very, very likely that UVC is going to perform against SARS-CoV-2. There's nothing to suggest it wouldn't, and we know it's susceptible to UV sunlight. So I think it's a fairly safe bet that it's going to kill it. We just don't quite exactly know how much. Where do you apply your UV? So you could put your UV in the ventilation supply air. This works if you've got a recirculating air conditioning system. It doesn't work if your contaminant source is in the room. So if this person here is infected and wants to infect this one, it doesn't really matter if the air is clean or not, because it's not going to disrupt this. So you can put in-room devices in. These are much better at controlling local contamination and local transmission. And we can do these in many different ways. So we can actually have it installed a little bit like an air conditioning unit. We can have a simple device, which is like a plug-in consumer device, the type of thing you would go and buy from an electronics goods store. And there is another alternative, which is upper room UV, which has an open field of ultraviolet above people's heads. how we use these, this is a real challenge, because we know these systems could, in theory, work. There's very little data on how effective they are in practice, and really need quite a lot of consideration rather than just simply buying a device and hope for the best. I think this is your picture, Azael, which is a picture of how you might apply it in an induct system, where you've got a UV lamp and the filters within an air conditioning duct, and it would depend on how many lamps you've got in there, the airflow rates, and the microorganism. And the upper room type installation looks a little bit more like this, where you've got UV devices installed in a space, and then you create this 3D light fields and there's a complex 3D airflow pattern within here. Last thing I'm going to show you is just some modelling from when we've looked at upper room systems. So this is a multi-zone model looking at infection risk in this is actually a hospital ward scenario, where you might have an infectious person in zone 1. You've got patient zones, which are 1, 2, 3, and 4, and then you've got circulation zones, which are 5 and 6. And we've used an infection risk model and also looked at energy consumption. And this was actually done for tuberculosis, but by sheer chance, the susceptibility for coronavirus is very similar. So I think the similar finding would apply. And we started off, said, okay, we've got 3 air changes an hour in this ward. What happens if we double the ventilation rate? And then what happens if, instead of increasing the ventilation rate, let's put UV disinfection in some different zones. So we put it in the infector zone, we put it in the patient zones, we put it in the circulation zones, and we put it everywhere. And we can see that here's our base case. If we double the ventilation rate, we halve the number of new infections, but we double the energy use. But if we install our ultraviolet in our infectious zone, what we find is we're nearly as good at reducing the number of cases, but with quite a marginal increase in energy. And if we start putting our UV devices into more of the zones, we get a better effect, but we still don't reach the energy requirement of the increase in the ventilation. So potentially it could be quite an energy efficient option. I would never advocate for reducing ventilation, but if you can't increase ventilation, then it's quite a good option. So just to finish off then, I think we know quite a bit now that SARS-CoV-2 is transmitted in close proximity, and that poor ventilation is a factor in this. There's loads of things we don't know yet though. So we don't know yet about the viral load in exhaled breath. I think that's a really critical piece of information that we need, because that's going to really tell us what we're dealing with in terms of how much is going to be put out there. We don't know how much you have to be exposed to get infected, so the dose response. We don't know the importance of the different transmission routes, and we don't know how these differ in different settings. So whether in a hospital it will be different to a community, whether it might be different on a public transport compared to a school or compared to an office. We don't really know yet the importance of the aerosols. I think at the moment we're applying a precautionary principle. There's growing evidence that they matter, but not every time. So it does seem to be very much the super spreading cases where it's likely to matter. I think we really lack evidence on the mitigation strategies, and it's very hard to get that. It's, you know, it's actually quite hard to run an intervention study and say, you know, the face masks made this difference or the ventilation made this difference, because we're throwing so much of it at the same time. It's very hard to separate things out. And then I think from a more sort of engineering space, I think there is a lot of potential for technology solutions, but there's a lot of gaps in knowledge of how the practical experience of how you deliver this and how you deliver it safely. I mean, there are loads of technology solutions out there on the market. Some are probably very effective, some are safe but ineffective, and some are actually dangerous. And we really don't have a good handle yet on which of those there are. And the marketplace is moving faster than the science on this, which is a bit of a challenge. And I'm going to stop there. I've talked for far too long, but hopefully you've got some time to ask some questions.
All right.
Okay.
Thanks a lot, Cath. Really, really interesting. So I'm going to open the microphone for some questions. I have some questions. If someone has any question, please open the microphone and go ahead. Feel free to ask.
We have some questions in the chat.
Okay.
Maybe we can
start with that. There is one question from Silvia Iliana. She says, how long does the virus live in cold environments?
So we don't know yet, but it can be days, we think. I think I've seen a study from Australia which said 28 days. Now that was a lab setting, so it's a very controlled setting. But we do know that, I mean, if you're a virologist and you want to keep your virus nice and safe, you put it in the fridge at 4 degrees C. So we do know that at low temperatures, it will survive quite a long time. I think in Mexico, you may be a little luckier than us. I think you may have some higher temperatures than us over here.
Yes, well, we've been over 35 degrees for the last 3 months, and we still have a lot of infections. So
yeah, but have you got it in indoor spaces which are air conditioned?
No. What do you mean, like to have that temperature in indoor spaces? No, we have the air conditioning.
No, so you've got people go inside with air conditioned spaces.
Yes,
probably quite low ventilation rate because it's air conditioned. Yeah.
Yes.
So,
public transport.
And you saw the same in the southern states of America.
Yeah, public transport, I think, well, we don't know because there is no evidence or reliable proof, but there is the suspicious, well, we suspect that public transport is causing a lot of infections. To be cramming in the public transport, but we don't have evidence, we don't have data on that.
That's quite interesting because here there's suspicions that public transport isn't causing very much. But I think that's because our transport has been reduced quite a lot and the numbers have reduced, and it's mandatory to wear face coverings on public transport, so which makes a big difference.
Yeah, actually, here we had that, we did that, there was a reduction in public transport. What I think it was worse because then what happened is that there were very little transport units. So every transport unit was packed. So we had a lot of people in close contact. Instead of stopping people from traveling, what happened is that everyone traveled in the same bus.
Yes.
So we have one question here from Alejandro. It says, with regards to the health impact, yeah, some people have suggested that this might not be a pandemic, but rather a syndemic, which will affect the approach in order to solve the problem. Has that been discussed as an alternative over where you are?
I'm not sure what you mean by syndemic. Do you want to say?
Alejandro, go ahead, open your microphone if you wish.
Okay. Hello, I'm a bit sick of the throat, so I don't know if I'm fully clear, but so a syndemic is sort of like a synergy of different epidemics, and they do this in the sense that they say that it's not really because of precisely that thing where BAME people and older people and people with already pre-existing conditions are more likely to suffer casualties under COVID. There's that it should not really be treated as a pandemic in the sense that it should be addressed solely as COVID, but more so that it should be addressed as a endemic where the underlying causes that worsen the impact of COVID should be addressed before the disease itself so that it mitigates or reduces the full mortality rate that the disease has.
So I think that has been discussed to some extent. I think it's challenging that. Obviously, some of the conditions you can't mitigate because you can't mitigate age and you can't mitigate ethnicity. There are discussions about mitigation, for example, around diabetes and obesity. The timescales are just not going to work though, because it's not feasible for people to for us to tackle those conditions before because the virus is already here. I think you're right though, in the way that there are multiple epidemics going on, and you see that you get an epidemic amongst, for example, amongst university students, but it doesn't necessarily spill into the community. You get an epidemic in care homes, you get an epidemic in hospitals, and they all interact together rather than being a single epidemic that affects everybody equally. And of course, you've probably seen there's a lot of debate about whether you can shield people or segregate society, shield the vulnerable. I think there are a lot of issues with that. It's a great idea in theory. In practice, it's very, very hard to do because our society is very much more integrated than we think it is. And I think there are also issues that there's growing evidence that people tend to measure deaths, but actually there's an awful lot of people who suffer significant ill effects but don't die. So either in hospital or even not in hospital, there's a growing recognition of what they call longer COVID, where people are suffering significant health effects months later. And many of those were previously young and healthy people. I think the other thing that's a bit worrying is that there's evidence that immunity doesn't seem to last. So we've had several cases now worldwide of reinfection. There's maybe a hand, it's still a small number, but it does sort of suggest that immunity lasts only 3 or 4 months before you're now susceptible to it again, which means that it's going to be very difficult for immunity to play a part.
Sounds challenging, or is going to the way ahead sounds a bit challenging. So we are about to go back into indoor spaces. We're about to go back into the university classrooms. We have people here from industry who right now is working from home, but they are in the process of planning about the safe return. Well, this is a question. What tips or recommendations could we give them to take care for a safe return? What will be the priorities points to take care for a safe return?
So I think the one I would say is to make sure you mitigate all the transmission routes. So we're tending to talk about 3 transmission routes: surfaces, aerosols, and close range, which is a mixture of aerosols and droplets. So you mitigate the close range by distancing people, you mitigate the aerosols by ventilation, you mitigate the surfaces by good hand hygiene and surface cleaning, and you mitigate them all by source control, like face coverings, like having good processes for trying to stop people who are infected coming into work. I think there is a risk. I mean, one of the real challenges is you need to have systems in place that if people have symptoms, that it's okay, or if they think they've been exposed, that it's okay for them to not come to work. Because anything where that's very much behavioural, but anything where there's an expectation that people will go to work, or they have to go to work for financial reasons, your system falls apart then and it breaks. So actually having good systems where you know who's there, who's not there. I mean, the other thing is, you might want to reduce occupant density in spaces, and rather than having, one person in on Monday and a different person in on Tuesday, and then the same first person back in on Wednesday, actually put people in cohorts, put them in teams. So, maybe have people in for 1 week and then a different team comes in the second week. So you're always exposed to the same people. You're in like a bubble then. And it then means that if there is transmission, you're transmitting it only within your small team rather than the whole of your office.
So
there
basically,
are some quite practical things you can do.
Yeah, to take at least one action in each one of the lines of transmission, and then a system where we can detect and we can allow people to well, stay at home or work differently if they've been exposed to some dangerous situation or compromised situation. And
Yeah.
in that, well, I found really interesting about the air ventilation. What would be a good, what would be a good air ventilation for a indoor area?
So we've looked at this. It's hard to say what's good. It's easy to say what's bad. So we were looking to, if you use carbon dioxide meters as a means of measurement, we've said that if it goes above 1,500 parts per million regularly, that space is poorly ventilated and you would want to do something about it. And that's a pragmatic thing, because it's not feasible to improve the ventilation of every single space. So it's about the thing to do is identify those which have got the poorest ventilation and mitigate those first. If you do have the capacity to improve ventilation in other spaces, then great, it's definitely a good idea to do it. And I would say try and keep your carbon dioxide below about 800 to 1,000 parts per million if you can. That's a good, to give you the best option. And if you've got spaces where people might be speaking loudly, singing, doing aerobic activity, I would have much higher ventilation rates and try and, actually do those activities outdoors or reduce them significantly, because they're much higher risk.
Okay. So, for example, above 6 air changes for, could we put an air changes per hour number on there?
Yeah, it's not totally straightforward to put an air change per hour on it. So for smaller spaces, yeah, something like 6 air changes an hour is good. If you think of a really big space, think like a really big supermarket or something. Actually, they have quite low air change rates, but because there's so much air there, it makes it safer, because you've got this sort of really, and it's very transient what happens there. Okay, so it's a bit more complicated than just a number.
Okay, so we have two more questions here. It says Christian. It says, with the new waves of coronavirus growing, seeing that people won't quarantine and are tired of the restrictions, is the only solution to wait for the vaccine and let the numbers continue growing? What can governments do that they haven't before and that people will accept to do?
Yeah,
I think that's a difficult one.
That's very, very hard. People are tired of the restrictions. The problem with you just let the numbers grow is you overwhelm your hospitals, and you end up with a lot of deaths, and that's difficult as a society. I think we have to keep trying to keep the numbers down, so we shouldn't just let it give up and let it grow. I think we should be putting in what we can, safe. If you look at outbreaks at the moment in the UK, there's a lot of outbreaks associated with universities, and nearly all of that is in student accommodation. It's actually very little evidence of transmission on campus, because the campus has been made very, very safe. So I think if you set your environments up carefully, you can make them safe. It's a disease that has real inequalities in it, though. So there are some people who are able to be safe very easily, and there are others who are exposed because their housing, their work, everything is against them. And that, it exposes all the inequalities in society, which is a real challenge.
So, Kat, for example, I went to the gym after many years for the first time, and I was alone. It was at night. There was nobody at the gym, nobody, just the person in the entrance. And he told me that I had to wear the mask. And I was like, but why? I mean, I'm alone. Literally, there was anybody else. I told him like, why should I wear it? And they were like, oh, those are the rules. At that moment, I thought that it didn't make any sense. But do you consider that actually it makes sense to still wear it?
I think it potentially does. I mean, it is hard to, when you're in a very, you're very spaced out. It is harder to see, but if you had it, you would potentially be contaminating the gym equipment for the next person.
Right.
So I think we need to think about the masks being there. I protect you and you protect me, sort of scenario, rather than we each protecting ourselves. But it is tricky, that one.
We have one final question from Jasmine. This is, please, could you give us some examples of changes that are planning to be taken in architecture and engineering, especially in hospitals?
So, yeah, I'm not sure exactly what changes are happening. I am aware that this has thrown a light on ventilation, that people are starting to realise that ventilation is a lot more important than they thought it was. And that poses, again, a really interesting innovation challenge, because now, for many years, we've focused on energy as our priority for ventilation. And maybe the past 2 years or so, people have been thinking, oh, air quality matters. And now suddenly ventilation matters for infection transmission. And so actually we've now got to think about, how do you innovate to redesign buildings, existing buildings, to be energy efficient and thermally comfortable and have good air quality and have good ventilation for infection transmission. And that's a really hard ask. I think there is a very big interest in air cleaning technologies. And the challenge there is, what evidence have we got that they work? And how do you make them happen safely? So what's the right, guidelines, best practice, etc., for deploying these things? How do you maintain them? How frequently do you change the filters? How frequently do you change the bulbs? How do you know that you've bought a good system or a really dodgy system? So I think there's some real engineering insight in there. I think people are thinking much more about airflow patterns. They're thinking more about movement of people as well, and the design of spaces to, we went through a period of hot desking, and perhaps hot desking and open plan offices is less desirable than it used to be. But we then need to think about, how do you balance that with not wanting to put everybody back in individual offices and things. So again, I think there's some really interesting opportunities for how you design the internal space in buildings. And we should use this as a way of saying, how do we make spaces that are better for people?
I think that's a really good a starting point for our next innovation challenge at the Innovation Gym. How can we redesign the indoor spaces for air quality control and energy efficiency? So we might take that. Cath, thanks a lot for your time. And I wanted to say something as well. Recently, you were recognized with the OBE. Is that correct?
Yes, that's right. Yes, thank you.
Amazing, really, really amazing. OBE is a recognition given by, is it I don't know if it's the government or is it the Queen, or is
it's the Queen technically.
Amazing. Well, if you go there and have tea with the Queen, please send us a picture.
Yeah, I will do. One day I might get to go and visit the palace, and they might give me something, so. Which is kind of nice.
You get to meet the Queen. All right. Yes. Andy's saying that you are going to meet the Queen, so we want to see the pictures later. All right. Okay. So thanks a lot, Cath. Really, really thanks a lot. We recorded this masterclass, and we're going to put it online for students and the general community. And well, it's been really, really interesting. And by the way, we're still working on UV sterilization projects here at Tec de Monterrey.
Yeah.
Where we're working on a device that is going to be ready hopefully in the next 6 weeks. And the paper, we still have the paper to
I know you
to finish.
knew you were going to ask me to read that paper.
Andy's here as well. We have
Yes.
the paper there. Yeah, there is the susceptibility of coronavirus there in that paper. All right. Okay. So thanks a lot. Thank you everyone for joining, and see you in the next masterclass really soon. Okay. Thank
Thanks,
you.
Rafael.
Cheers.
Thank you. Really nice
Bye.
to see you. And
Nice
thanks
to see
everybody
you.
for joining.
Cheers. See ya. Bye.
Bye.